what we have really quickly is relating the relativistic momentum and relativistic energy equations. That's what we have here. So we know that our expression for relativistic momentum, you can say it's PV, you can say it's P prime, you can say it's P. I wouldn't recommend that. That's too much. That's too similar to the classical equation. But for the purposes of this video, we use PV equals mv on our friendly little expression here that we've grown so close to. It is the classical equation mv multiplied by the Lorentz factor. What we have for relativistic energy, we can say E or E prime. We're just going to use E here, is equal to mc squared on, once again, the same little factor, v squared on c squared. Now, what we want to do is make m the subject of both. And we'll draw a little separating line here. So we have 1 on pv equals 1 minus v squared on c squared, mv 1 on e equals this 1 minus v squared on c squared on mc squared. And then we just do a little swap. So we go m up here, swap m, go pv, this 1 minus v squared on c squared on v. Then we go here, m equals e, 1 minus v squared on c squared on c squared. And now they equal each other. They both equal m. They both equal m up here behind the color wheel. Now what we can say is PV 1 minus v squared on c squared on v equals e root 1 minus v squared on c squared on c squared. Cancel both of these. And I would like to put, so that's momentum, I would like to keep our constant on one side. So what we do is we go c squared PV equals VE, and we get our constant on its own. C squared is a constant, as we know, always not affected by relativity, the speed of light. PV, a bit hasty, VE, velocity times energy, on PV equals c squared. What does this say? Well, it describes a relationship between these. It also says that if any one of these quantities were to reach or exceed the speed of light, infinity, if they were to approach infinity, it will completely negate this, because c squared is a constant, and if any one of these values were approaching infinity, then the constancy of c squared would be broken. And as we know, as PV approaches, as V approaches C, PV approaches infinity. Right? And what we also know is, as well as when V approaches C, PV approaches infinity, we also know from this exact same observation, as V approaches C, energy approaches infinity. Now, if any one or multiple of the values or variables in this right-hand side were to approach infinity, you simply cannot have a constant c squared, because c and c squared have no direct correlation with being equal to infinity. You can't have something equal to infinity. That's an undefined value. Therefore, because of the relationship, by making mass the subject Oh, that's an eraser. By making mass the subject of both of these equations, you can derive the fact that now there's a relationship between velocity, energy, and relativistic momentum. And in this arrangement here, they equal c squared, which is a constant.